Hello everyone, my name is Ma Xiaochen and I'm a PhD student from the Hong Kong Polytechnic University. Today, I'm glad to give a presentation titled Effect of Spring Nozzle Parameters on Surface Wettability and Performance Improvement of Indirect Evaporative Cooler. Today's presentation will be divided into 6 sections, and let's start with the first part, the background. From this figure, we can see in China, the cooling energy use has been growing really fast and reached nearly 400 terawatts in 2017, accounting for 1 to 5 of global cooling energy use. And from the red figure, we can see in Hong Kong, the electricity end use for air conditioning increased by 15.3% in past 10 years, and it's about 30% of the total electricity use in building sector. And in order to face the cooling energy use status in buildings, it's important for us to develop the more sustainable cooling technology. And one of the technology called indirect evaporative cooling has attracted a lot of attention recently. The IEC technology is green and energy-saving technology that uses water to evaporate and absorb heat for cooling. For the conventional IEC, it always used for sensible cooling dominant building and dry climates. But for the hot and humid regions like Hong Kong, it also can be used as an energy recovery unit. And for both of these two working principles, the key point is the evaporation of water into air. And when we talk about the evaporation, a definition called wettability should be introduced. And for the wettability, if the lower water supply, it will lead to lower wettability and cooling capacity. Well, if the water supply will be higher, it will lead to higher film thickness and thermal resistance. So it's important for us to find the balanced value for achieve the best wettability. Because of its importance, some studies have been carried out recently, like change the different plate structures from A to E and change the airflow and water flow directions. There are also some experiments about different types of nozzles, and we can have the results comparison like this figure. But there are still some research gaps. First, the optimization of surface materials and structures often requires more complex processes, costing human and material resources. And second, the existing studies discussing improved water distribution are not yet well developed. Next, the spring water droplets in unfavorable sizes can cause the drift, in which the liquid particles are carried out by the living air stream without evaporation. And last, the water membrane on the plate surface will not be ideal because of the water surface tension and different nozzle working conditions. So in order to cover the research gaps, the aims and objectives was proposed. First, we developed a 3D CFD simulation model for the description of water spring distribution and the formation of water membrane. And second, to carry out the nozzle experiment to do the validation work. And then, evaluate the effect of different nozzle parameters. Next, to carry out the parameter analysis of spring setting on the IEC performance. And last, the optimal value and setting parameters will be achieved. And then, to achieve the proposed aims, the research method was introduced here. First, the model of single wide channels was set up. And then, to clarify the different heat transfer for different coverage area, a factor called coverage factor was set here. And the factor can be defined as the wet area divided by the whole area. For the model equations, it can describe the working principle of the IEC, and it contains the conservation of energy, mass transfer, multi-phase model, and EWF coupled DPM model, also the model transfer. And to carry out the simulation process, we should divide the plate of experiment scenario and simulation scenario into the same number of grids. And the ICEM software in ANSYS was applied to the mesh model. After the grid independence, we can get the accurate grid number to be decided as a simulation number for further research. Besides, in order to evaluate the performance, we should introduce the different types of indexes, like water distribution, cooling potential, and IEC performance. And to support the validation work, the different types of nozzles and the test instrument were selected according to this table. And from this figure, we can see the experimental bench. Some conditions were fixed, showing like this, and the requirements contains the outermost transparent casing to support us can see the water membrane on the surface of the plate. And the sliding nozzles was mounted on top to test the nozzles at different positions. And then we can have the validation results. From this figure, it shows the maximum discrepancy is 7.1%, which was acceptable for the further analysis. Based on the verified model, we can have the results and discussions. For the first part, about the influence for single nozzles, we can see if the spring droplet diameter is different, we can get a different coverage area. And from the trend figure, we can see it will increase first and then decrease. And it have the highest value at 0.05 millimeters. And the reason is that the droplet flow is countercurrent to the airflow. Also, when the droplet diameter is too small, it will be blown away before contact with the plate surface. Well, when the droplet diameter is too large, it will slide out of the wet channel before making contact with the plate surface. And similarly, for the different spring cone angles, it also will have different coverage area. And from this figure, we can see it increase first and then decrease. Same. And the reason was increasing the spring cone angle increases the droplet coverage area, but decreases the density. So too large a spring cone angle can lead to over-dispersed droplets, while too small a spring cone angle will affect the uniformity of the spring distribution. What's more, for the influence of multiple nozzles, the optimal injection parameters are adopted at the top of real-size IEC, and 0.05 millimeters will be used as the fixed droplet injection particle size. And from the figures show the influence of nozzle distance on coverage ratio, we can see the distance is 160 millimeters can achieve the best value. So the spring of nozzles are too far apart, causing some droplets to escape from the boundary, while being too close causes a large number of spring droplets to collide and splash against each other. And for the influence on IEC performance, when we apply the wettability to the wet bubble efficiency, we can see when we have the droplet diameter at 0.05 and the distance between two nozzles are 160 millimeters, we can have the optimal coverage ratio. So change the spring droplet size can achieve an increase in wet bubble efficiency from 34% to 51% by affecting the coverage of the water membrane on the plate surface under the same operating conditions. And last part, the conclusions. To conclude, the water membrane coverage ratio has the highest value when the spring droplet diameter is 0.05 millimeters, and the value of coverage ratio is 0.22. Second, when the fixed distance between two nozzles are 160 millimeters, the coverage ratio of the water membrane on the plate surface is optimal, which is up to 0.52. And then, for the IEC with 400 length and 260 width, two nozzles set 160 millimeters apart in the nozzle particle size of 0.05 millimeters can achieve the maximum wet bubble efficiency of 51%. And last, to summarize, by appropriately setting the spring droplet parameters to influence the coverage area of the water membrane on the plate surface, the wet bubble efficiency of IEC can be increased by 17% under the same conditions. And that's all. Thank you for listening.